as we registered on Friday, so we were unable to obtain the class measurements. For part 1, we were able to obtain the MOSFET characteristics for part 2.
And these are the MOSFET characteristics. This is the gate voltage sweep. This is, as you can tell, is exponentially increasing, so it's not entirely linear. The saturation increases as voltage increases. This is probably due to early effect and capacitance. And this line here is the best fit. We basically did this for all the MOSFETs. This is a gate voltage sweep PFET, decreasing, and if you look closely, you can see a red line representing a best fit, which is used throughout. This is the source voltage sweep NFET, PFET, drain voltage sweep NFET, PFET. We did this to gather data, so we can calculate these values. Kappa, threshold voltage, I naught, thermal voltage, and sigma, which Maggie will explain how she calculated.
So we're able to calculate the following values by deriving the following theoretical model by assuming that sigma is equal to 0 for the gate voltage sweep and the NFET. And we're also able to plot the drain current versus the gate voltage, and we're able to determine the kappa based on the following slope of this curve, as well as the threshold voltage as the point where the device changes region, as well as I naught based on the following equation. And for PFET, it is very similar to the NFET, except for the substrate was at VDD, and similarly we were able to determine the following values. For the source voltage sweep for the NFET, we also calculated the theoretical model similarly. And in this case, we were able to determine the thermal voltage from the derivative in this region. Fortunately, it's a little bit larger than the expected value at room temperature, which is about 25 millivolts. And this is because we made some assumptions about the fact that sigma was equal to 0. And then for the PFET, it's very similar as well, except for the substrate was at VDD, and we were able to calculate the following parameter. And then for the drain voltage sweep, we couldn't assume that sigma was equal to 0, but we were able to plot the drain voltage versus the voltage drain. And what we found was that sigma was approximately equal to the derivative in this region. And similarly for PFET, we found that sigma was this value.
And moving on, we have the source power Simulink. It's an arbitrary generator going to common drain as Vin and DC voltage or bias voltage as Vtal. DC voltage, we varied that between 0.2 volts and 0.5 volts, and we got data here. The blue graph is 0.2 volts, and the red line, the blue and the red line is 0.5 volts. Interesting thing we saw was that as we increased the bias voltage, we decreased the response, as shown here. Other interesting things that we calculated from this is kappa, which we found to be linearly proportional to V out, but kappa is inversely proportional to depletion capacitance. And then after that, we went to look at high gain amps. This is a Simulink for a high gain amp, common source and only an arbitrary generator. And then what we gathered from that was this. The blue line represents a 50 millivolt step, while the red one represents a 1 millivolt step. These linear lines represent the best fit curve. We see some disturbance that we believe are due to non-linear, like early effect and capacitance. And we see that it's a sharp transition from ohmic to saturation. Ohmic has to be less than source drain voltage less than source to gate voltage minus threshold voltage, but saturation has to be greater. And Maggie will explain the derivations for this.
Okay, so we were able to determine the gain from the following current, or from the following circuit. And what we noticed was that the gain in the high gain amplifier was dependent on 1 over sigma, which is a very large number, which is why it has a much higher gain than the source follower. And we're also able to calculate the bias current based on the following equation and the following assumptions.
And moving on, we have transconductance amplifiers. The first thing I wish to show you is the OTA. You can see that an arbitrary generator and a DC voltage go into an OTA. But the follower source that we focus on, we have an arbitrary generator, but no DC voltage instead we have a feedback loop and an OTA buffer, which helps to analyze the chip's dynamic behavior. And then the data we gathered was such as this. The regular OTA with the DC, you can see is increased rapidly and then flattens out. But the follower is very linear. You can see a best fit curve fits pretty well into it. And now I'll leave it to Maggie to explain the gains.
So the gain was just the derivative in the linear region, which is approximately 1.091 volts per volt. And we also noticed some nonlinear behavior as the device approached zero, which is due to capacitances, power dissipation, leakage current, and thermal effects.
And moving on, we have follower integrator. The follower integrator Simulink is exactly the same as the follower source, except that we have inputs of 40 millivolt step and 100 millivolt step. And we also changed the bias current from 0.5 nanoamp and 1 nanoamp. This is a 5 nanoamp 40 millivolt, 1 nanoamp 40 millivolt, 0.5 nanoamp 500 millivolt, and 1 nanoamp 500 millivolt. And Maggie will explain the rest.
Okay, so we were also able to determine the time constants based on 1 over the slope in the linear regions. And so we were able to calculate the following time constants in the following integrators. And what we noticed was that the transitions are steeper when the step input is increased due to the increase in bandwidth.